I'm going to talk about one specific project mostly in my presentation today on our Stever Road. This is kind of the outline of what I'm going to cover. So we'll start with the background information. Most of you here are county engineers, so it's always nice to kind of get a picture for where we're working so you can relate. This is where Defiance County is located in Ohio. You can see some of the statistics about our county there. In Ohio, anything over 10 feet is considered a bridge, but I know for most of you, you go with the federal definition, so we have about 105 that are over 20 feet. And one of our problems, which most of you probably relate to, is for our federal funding for larger bridges, we have about a 6-year wait. And sometimes that doesn't time out with how a bridge deteriorates. So that's kind of one of the issues that we faced here. We're catching up in our county, but obviously you can see that most of what we're replacing is fairly old. This project utilized GRS for the foundations, and I'm not going to cover it in great detail here, but just in case some of you haven't been exposed to that before, I'm going to give you a brief explanation of it. GRS, geosynthetic reinforced soil, is actually a construction material. It looks a lot like MSE, but there's some fundamental differences. Closely spaced sheet reinforcement made of geotextile, combined with compacted gravel, with some sort of a facing element, is a construction material that's very easy to use. And what's nice about it, you can see us in our garage facility here doing a large-scale test after we built a number of structures, is you can get a very predictable behavior from the material, just like you can from a concrete or steel. It has a linear stress-strain curve, has a very high capacity, much higher than we actually need for a bridge abutment in most cases, because you can see down toward the bottom end, and we'll see this graph later in the presentation, where we're actually loading, it's very, very far down on its capacity curve, or capacity line. And so basically, we're going to go into this with the assumption that if we build these this way, it will behave in the way we predict, and it's a very low cost and fast construction method. And that's really true with a number of aggregates. So for those of you that are interested in using GRS for bridge abutments, while the slope on that line might change depending on your aggregate, it's a very predictable material. I'm going to go through this project in some of the details. It was a 130-foot truss on old sandstone abutments. We'd had some history of deterioration there. In fact, I think one of those floor beams was on its 3rd floor beam in the life of that bridge. It was load posted, and we needed all of that opening. It's on a fairly large channel. Some of the upstream structures were multi-span, and we have debris problems there. Very wooded channel, and you know, it's not uncommon to get a 50 or 60-foot log kind of wedged between piers, and so if we could stay with one span, we wanted to. The structure that was there did occasionally overtop, so we wanted to raise the structure if we could. And this is one of the rare spots in our county where we actually had bedrock just a few feet below the channel. What we decided to go back with was to keep the opening just like we had with an 130-foot opening, so we didn't have any channel obstructions. And using the GRS IBS abutments that we had done a number of times with smaller concrete spans, we were pretty sure that this would give us the ability to build those abutments vertically, load-bearing, and very quickly. Ohio's a little unique. Maybe some other states are this way, but usually the states use the federal research money on bridges, but in Ohio, they pretty much leave that to the locals, which I'm not always sure is a good thing because many of us don't take advantage of that, but we decided to in this case. And that program will pay for the innovative portion of a project at 100%. And so I was able to kind of partner that money, which has about a 2-year turnaround, with some state grant money that is available in Ohio. And so I kind of broke down the sources of the funding there. What we decided to do was build the abutments ourselves using GRS, and use the federal money to pay for basically the steel beams, the state money to pay for some of the rest of the superstructure and the approach roadway. And so it's not quite as nice as 80-20 money, but you can see that we were just a few months over 2 years from the concept to construction, which I couldn't come anywhere close to with the federal money, and I had to do something fairly quickly here. I'm just going to quickly flip through the plan sheets so you can get a feel for what the structure looked like. It was about 25 feet from the bedrock to the deck, top of the deck. And we softened the curves that were out there so that they would be safe at 55 mile an hour. We have about 1,500 ADT on this road. Five lines of girders, and these were plate girders. And this is the foundation plan, the GRS abutments. So again, that abutment is made of compacted gravel with sheets of geotextile and split face concrete block facing. There's kind of a zoom in on the details of how that's constructed. So you can see we have about a 6 foot wide, and many of the things that you would have learned in MSE design really don't apply here. A lot of the base to height ratios really aren't there. Again, this is a material with very predictable linear stress strain curve, and so if you go to the design manual that's now out, you'll see some of those guidance that's there. In this case, it's about an 8 foot, it was designed to be about an 8 foot bottom excavation. I think in reality it ended up being a little closer to 10. But one of the beauties of this, because you're basically filling it with materials that are very modular, gravel and fabric that comes in rolls, you can adjust to those kind of changes very easily. And then what we did at the top, we had set it up originally to allow them to use precast panels to set those beams on. You see the hatched area there. There would have been a precast panel for each beam. In reality, that was not their critical path, and so they chose to use a cast-in-place slab in place of those individual panels. And then we had holes in the end of the girders to kind of lock the ends of that in, so it was something along the lines of an integral abutment, although there's really nothing other than friction tying it to the substructure. There's a zoom in on that. You can see there we had hoped to use galvanized girders, but with the cost, ended up switching them to weathering steel with the end 10 feet painted. Now this was a research project. We did apply for research money, and so here were some of the goals that we were trying to accomplish in the research. Again, this structure had 140 foot long steel beams, so we had a much larger thermal movement that we were predicting, and so we wanted to investigate how that would be accommodated by these abutments. We wanted to investigate, that movement would, in theory, produce some pressure from the GRS mass behind the back walls. And from the load test, we had a predicted settlement from the dead load and wanted to investigate how that would compare to the actual. And then this was also an opportunity through the project to demonstrate the viability of GRS as a foundation for a very large structure. Many of the other structures that we'd done were smaller. The largest before this was an 80-foot beam. And then also to demonstrate how a steel superstructure would be compatible with GRS and the integrated bridge system, where we used that same GRS fill behind the superstructure. And then also to demonstrate the speed of construction. So here's some shots of during construction. There's the excavation, and there's actually rock under the water there, but we haven't pumped it down yet in this picture. There we temporarily pumped it down and put down the sheet of geotextile, the gravel fill, compacted it, wrapped the geotextile back over, and then we're put down a very thin layer of leveling stone. That's usually something less than a ½ inch. And so you can see them there leveling the first row of facing block. In our case, this is a little different than some of the other counties that you saw present yesterday. We in most of our cases generally build our abutments brand new from the bottom up. We don't save anything of the old ones in general, although I'll talk a little bit about the possibility of that. And so basically that fabric sat on the bedrock, wrapped it around, and then we're laying out the first row of block there. Once the first row of blocks in, you fill behind it with stone and begin compacting, and then it's like you heard in previous presentations, block stone fabric all the way up. And so there we are at the end of the first day of construction. And in our case, we use, depending on the size of the bridge, 5 to 8 rows of colored solid block that we cover up with our rock channel protection, so that if any movement of the channel rock occurs, that we can monitor that. So you don't see any of that red block on the completed structure unless rock moved in front of it. This is a shot on the other side, so you can actually see the top of the bedrock. a picture of the excavation. There's a picture of the sheet of geotextile that we put down, and you can see that the rock surface was irregular, so we put in a scrap of fabric there. So again, we didn't exceed that 12-inch thickness. That's a part of the design. And so there we are. Basically, that's about 3 days into the work. And so another 2 days and we'll be up to the beam seat. And one of the other beauties for us, you can see that the water's up probably 5 feet from where it was when we started construction. And as long as you can build faster than the water comes up, you can keep right on rolling. We laugh, but that's been an amazing advantage for us. Many times water would shut down our projects, and we basically need one good day to stay ahead of the water, and it really doesn't matter. You can build this in the rain. It's an open graded gravel. So there's an abutment ready for the bearing pad. This is actually the south abutment. The previous picture was the north one. And each of those abutments took about, from the time we finished the excavation, took about 5 days to get to that point. Then the contractor, basically we left the project for a while. The contractor came in, formed the bearing pad. You can see the bearing pad there ready. You can see him bringing in the beams, and in this case, like you saw in earlier presentations, they chose to put the cross frames in, assemble them on site, and set them in pairs, with the center beam being set last, where they could bolt the cross frames to the adjoining assemblies. This has been one of the great advantages for us with GRS. Really, that whole mass is built the same way as the beam seat is. And so you can load right behind the beams, right behind the bearing area, the same way you could load the beam seat. And so we have had a lot of skeptical crane operators come to these jobs and say, you want me to set my big crane up on what? But usually when they leave the job and don't find any marks from their crane pads, they're a believer in the capacity of this. Because that big crane has about 250,000 pounds just a counterweight. So there are the beams set. Then what followed that, the back wall that tied the ends of those beams together was poured. And basically then that let them continue with the deck forming and let us come back in with our crew and complete the GRS fill behind the beams. You can see that GRS fill complete with the cap poured on the top of the blocks, and here they are pouring the deck. And there's basically what the completed structure looks like. This was a research project, and so there's some strain gauges there, and you can see where some of those wires come out and go to a data collection box. Here's a little bit what the project schedule was. Again, from my standpoint, we weren't terribly worried about schedule. It's pretty typical for us to just close a bridge and take whatever time it takes just to get it finished on our road, since the traffic doesn't tend to be very high. But you can see how some of the normally critical path things went very quickly on that schedule. It took us basically 5 months to finish it. We'll kind of go over some of the results now. The thermal cycle was the big question. Would a structure this large really be compatible with these type of abutments? And that's been a very encouraging thing as we see the results. The thermal cycles were about 1.5 years old, have been very compatible between the substructure and superstructure. The pressure gauges on the back of the back wall are showing very, very small pressures in the range of 1 to 2 psi. And the forces in the girders, based on the strain gauges there, are also very low. And the settlement was very, very much as predicted. And that settlement basically all happened at the time we cast the deck. There's about 600,000 pounds of concrete in that deck, and so the structure moved down that stress strain curve just as would have been predicted. And so we were pretty happy that the GRS on a large scale is comparable, very comparable to the small scale. I mean, like I said, there's about 600,000 pounds of concrete and 250,000 pounds of steel in that superstructure sitting on that gravel and fabric. And it's behaving just like we predicted it to, based on the theory. It took us about 5 days each to build the abutments up to the beam seat, and it's had very good performance so far. There's a picture a year later. And this has been sort of the surprise to me. When we designed this, I really expected that we would have to do something to accommodate the movement between the superstructure and the substructure due to the thermal cycle. And so we put a little notch in the back of the concrete deck. I popped that little piece of the plan up there so you could see it. And so the actual back of the abutment is 5.5 inches away from the actual interface between the concrete and the asphalt. And this is a picture 1 year after construction of that joint. So you can see where the snowplows shaved a little bit of the asphalt and pavement marking off where it wasn't just perfect. But you can see where that crack seal material that was put in right away is still intact. And how there's, I really, to be honest, expected a crack about 5.5 inches back from that interface. And our planned repair was to just saw cut out about 10 inches of asphalt and put in a modified asphalt that would be a little more flexible. But basically, it seems like that the substructure is basically flexing with the superstructure, and they're very compatible with each other and not causing a problem at all. And again, basically, we have 5 bridges where we have monitored the settlement with the GRS abutments. This one is labeled on that graph, and you can see how they all fit very well with the sort of lab result of the capacity of the material. Here's some future thoughts based on what we've learned here. This integrated approach with that GRS, gravel fabric fill behind the beams, wrapped against the back of the back wall, is working very well, better than our traditional integral abutments with an approach slab. And so this is something that for everybody, even if no matter how you build your foundation of your bridge, you may want to consider using GRS behind your back wall in place of a approach slab. Because it's a very low-cost method that no matter what your bridge is founded on could kind of confine that fill behind and give you a better performance than an approach slab does. We have a number of bridges that the state built on a recent U.S. route that they made 4-lane in our county that are about the same age as this bridge and have substantial bumps already at that interface. And we do have plans on a kind of low-cost bridge replacement that we're working on right now to actually build GRS behind the existing abutments. In other words, leave the concrete abutment that is there now in place and go in behind it and just wrap face behind the concrete so that instead of bearing on the old concrete, which is of suspect quality, we're going to bear on GRS right behind it, but leave the concrete there as a facade. These are some structures that have, between 10 and 50 cars a day. Can't really justify putting a lot of money in, so we're recycling some steel beams and going to set them on a concrete pad on GRS behind the old abutment. Idea to think about if you have a similar situation. And then we're also working on an idea with a local steel beam fabricator to come up with a quick way to set these. If we build a GRS abutment in a couple days, you can set the beams pretty quick, and then the things that take a lot of time are the forming of the concrete deck. So to find a way to speed that up so it's compatible in terms of schedule with a concrete box beam. And so I know you can't see a lot of detail here, but I'm going to zoom in onto each of these details so you can kind of see what we're talking about. We'll be bringing in steel beams that would have brackets already set up to be attached to the beams, where you could drop in sheets of plywood for the forming from the top that would sit on those brackets, and then have a bracket off of the edge beams that would be attached to the guardrail plate, where you could bolt a side form on that would also sit between those. Then pour the concrete on top of those pieces, and then unbolt. During that time you have all the concretes curing, which is still time you can't really get away from very much, to deform. And then that same bracket would be used to attach the guardrail to basically speed those portions of the construction up. So that's the conclusion of my presentation.